So let's go back to that reaction we talked about before. So why is this reaction spontaneous again? Well, remember it's 3 moles solids going to 3-ish moles of solids dissolved plus 10 moles of liquid plus some gas. And it turns out that creates a decent amount of entropy. The change in enthalpy, it's endothermic, and so it has a positive delta H, but the delta S is positive as well. So let's plug in and see what is the change in free energy at 298 Kelvin, where we do this experiment. So it'd be 80.3 kilojoules per mole minus temperature 298 K, and the entropy, and I'm going to convert this from joules to kilojoules because we're going to be adding it to something that's in kilojoules. 0.428 kilojoules per mole Kelvin, and that's our delta G, and you plug everything in, you get minus 47.2 kilojoules per mole. So spontaneous at 298 K. So that explains it. That's the balance of enthalpy and entropy. So to think about this in more concrete terms, let's think about the spontaneity of freezing water at high temperature and low temperature. So we know that at low temperature, freezing water is spontaneous. Therefore, that delta G is less than 0, and the entropy of the universe is increased in that case. And so what about the change in entropy of the system? Well, the change in entropy of the system, the water is ordering, it's negative, that's a decrease in entropy. But the change in energy, the change in entropy of the surroundings is greater than 0 because it's an exothermic process, and we're transferring heat into the environment that way. Now at high temperatures, the change in entropy of the system is still the same. You're still ordering water by the same amount, but the change in entropy of the surroundings is less because the same heat changes the entropy of the surrounding less. And when you add these two together, the entropy of the universe decreases, and therefore delta G is greater than 0. You know, if this is negative and this is negative as well, then if T is very small, this essentially is negligible. And the change in free energy is due entirely to the change in enthalpy. Whereas at high temperature, this becomes essentially negligible. And if the change in entropy is negative, then a negative times a negative is a positive. Okay, so there's 4 possibilities to look at. So let's go through the squares. So if it's an endothermic process and it decreases the entropy, there's really no driving force at all, right? There's nothing that will make that reaction go forward. It's decreasing the entropy of the universe in every way, so it's never spontaneous. On the other hand, if it's an exothermal process that increases the entropy, it's always going to be spontaneous. Whatever temperature you're at, it's always going to be favored. If, on the other hand, it's an exothermic process with delta H less than 0, and it decreases the entropy of the universe, for example, freezing water, then it will only be spontaneous at low temperature. If it's an endothermic process, but it increases entropy, such as vaporization of a liquid to a gas, then it will only be spontaneous at high temperature. So those are the 4 situations. Recognize the sign of delta H, delta S. Remember, it's delta H minus T delta S, and think about what is spontaneous: negative free energy change.